Bam! Mr. Tarrou, in this algebra lesson, we are going to learn how to model a real-life scenario word problem with a linear function. And through the lesson, we're going to be using this example of a car salesman that makes part of their income based on salary and another part of it on commission. And we're going to be identifying what the independent dependent variables are, what are the units of measure, and then if you're like many of us, if you have a hard time creating an equation after you read a word problem, then we're going to go back and rely on something that you've been doing much longer than algebra, which is just basic arithmetic. And we're going to make a table here where we're calculating the pay of, well, this is in terms of, like, say you are a car salesman, so we're going to calculate your pay based on whether you sell 1, 2, or 3 cars, and we're going to allow the pattern that we see in that arithmetic to allow us to come up with the equation, this linear function that's modeling your salary. And we're then going to graph it. And maybe you have or have not graphed lines yet, but because this is a real-world setting, we'll need to discuss how do you label the x and y axis and what would be an appropriate scale. We're going to be discussing why was a linear function a good model for this scenario. Why is it that the equation of this line and the graph of this line is describing how much you're going to make as a salesman. And then we're going to do another example as another lesson based on the same topic, and I'll put a link to that in my description of this video that's going to have a little bit of a different look, a little bit more difficult to hopefully help you with more of your homework problems. So we'll be discussing again why, how can we identify that a linear model is a good fit for a word problem. And then we're going to answer a question of, just how many cars is this, do you need to sell to make a certain amount of money, and if you know how to find an x-intercept, let y equal 0, and a y-intercept, let x equal 0, and if you know that slope is rise over run, well, that's all good for just, graphing an equation of a line. But since this is going to be applied to a word problem, how do we interpret those values in the context of your problem? So let's get started. We have got, you are working at a car dealer that pays a monthly salary of $1,000. So no matter, whether you go in for 40 hours for the month or 200 hours for the month, you're going to make that flat income of $1,000. So what do you want to do? You want to sell a car, you want to sell a lot of cars because the dealer is also going to pay you $200 in commission for every car that you sell, an income that's based on, how much you're selling for the company. What is the independent and dependent variable? Basically, and why? Basically I'm asking you, if you've graphed lines before, you know that there's an x-axis and a y-axis. What is going to go along that x-axis and what variable is going to go along the y? Well, what is it we're even looking at in this problem? Well, let's see here. You're working at a car dealer that pays you. Okay, so it's something about pay. You're making money. And you're making money, yeah, you got a salary, but really, hopefully, if you're really successful, you're going to sell a lot of cars, which is going to increase that pay. So it's a relationship between your income and how many cars you sell. Well, an independent variable is an input value. It's the number that's going to go into an equation and give you out an answer, an output variable. And in some situations, it's kind of hard to tell what should be the independent and dependent variable. If your word problem has time involved in it, almost always the time is going to be the independent variable. And is there a variable that you can think of that you would have some control over? Well, you're going to have some influence in how much you make by how hard you work, but how hard you work and how you present yourself to your customers is really about the number of cars that you're going to sell. So the number of cars are going to be the independent variable. How many hours a week do you work? How are you approaching your customers and dealing with them to entice them to want to buy a car? So your independent variable are those cars. And the dependent variable, selling those cars and selling more cars is going to have an influence on your pay. Well, I don't want to say salary because I have the word, salary of 1,000, like there's a flat value of $1,000 a month. So your overall pay is going to be a combination of your salary and your commission. So your pay is the dependent variable. And I didn't write it out why, but I kind of verbalized that. The independent variable is often a variable that you have some control over, and the dependent variable is going to be the output or the answer that you get. And in case you forgot, another vocabulary word that goes along with independent is domain. Okay, so your domain value, that's D-O-M-A-I-N, if you're not sure about that, is also going to be your value that's going to go along the x-axis. And your dependent variable, another vocabulary word that goes along with that is range. So domain and range. And they generally, when you're thinking about a Cartesian plane, an x and y axis, independent is along the x-axis and domain is along the y. What are the units of measure? And sometimes this is a little bit difficult to kind of not connect with your quantity or your variables. I mean, your independent variable is the car, but you kind of naturally say, well, it's the number of cars you sell. So the unit of measure for the cars is simply, let's put this in blue, the number of. The number of cars. The units of cars maybe is a language you might want to include. And now pay is a little bit more obvious. I mean, if I live in America, well, I do live in America, excuse me, I get paid in dollars. Maybe if you're in Europe, it's or England, it's the pound, or the I'm just spacing out here about the well, okay. Instead of just taking time to try and think of it, where we live is going to depend on the type of currency that we're paid in. And right now I'm going to be saying that our units of measure are in dollars. Okay, so we've got our independent and dependent variables identified, reminding you which is going to land on the x and y axis. We talked about the unit of measure for each of these, and write out calculations required to compute your pay if you sell 0 cars, 1 cars, and 2 cars, and 3 cars. And again, this is only going to really be necessary if the textbook asks for it, or if you're not sure how to write the equation based on this word problem. So the quantity. Well, your independent variable we already discussed was going to be the cars. And the units, I mean, that's kind of like the unit, I mean, that's some language that some people use, the unit of cars. Or I sold this many cars, like I sold 17 units in a month. So I'm just going to write the number of and run out of space. And the dependent variable is that pay, which is going to be in dollars. Now, what if you sold no cars at all? Just, I don't know, for some reason, for an entire 30 days, you didn't sell a single car. I'm not sure how long you'd keep your job, but the way this problem is worded, you would make, you would still get a $1,000 check so that, you can at least maybe pay some basic bills. Now, if you sell 1 car, that's going to be $1,000 plus our $200 commission. If you sold 2 cars, that was $1,000 plus 200 plus 200. And if you sold 3 cars, that would be, of course, 3 200s. Now, if these numbers are simple enough to do in your head very, very quickly, and a lot of my students even, they can't come up with the equation, and then I start asking them questions like this, and they start rattling off numbers, and I'm like, no, I'm making the numbers easy for us to work with in class, but it's that the recognition of the pattern that's there. Write out that arithmetic so you can see the pattern forming to help you develop an equation, even if you can do the numbers in your head, because what happens with a problem that you can't do in your head? So what's going on here? What do all of these lines have in common? Well, your pay is based on every single one of these lines, regardless if it was 1, 2, or 3 cars, has $1,000 written in it because that was that flat salary. And then you can see here that, what is varying is the $200. For 1, I got $200 showing up twice for 2 cars, $200 showing up 3 times for 3 cars. So if we put a general value of X or C, and actually I kind of sort of hate to just write X and Y when I'm introducing these type of problems to algebra students for the first time. I kind of like to just write the word, hey, my expression, if you will, some textbooks will call it an expression, is the cars. How many cars have I sold? Well, it's 1,000 plus 200 times the number of cars. that's sort of like a general term. Now that you recognize the pattern, 1,000, 1,000, 1,000, okay, no matter how many cars I've sold, I got paid $1,000 once. And then the 200 starts to vary by the number of cars. And this is an exact match. 1, 1, 2, 2, 3, 3, so it's $200 times the number of cars. Some textbooks, when they put tables like this, would maybe on the side say, hey, give me an expression, a general an expression that describes this pattern that you're developing in the arithmetic. And then so the function that's actually going on, if we use some function notation, is your pay is based on the number of cars, and that is equal to what we see here, $1,000 in salary plus 200 times how many cars you sell. Or you might see this as y is equal to 1,000 plus 200x. But with the words, it's much more obvious where all the numbers belong. So now let's get to the next screen where we actually, let's see here. We already have the function written, so we're going to create a graph that represents the relationship between the number of cars and the pay. Well, we're going to graph that function, making sure to label the x and y axis. Of course, we hopefully remember that the x-axis is the horizontal axis and the y-axis is the vertical. And include a scale. Now, you'll notice that I have only included sort of like this first quadrant area where we have positive x's and positive y's, because that only makes sense in the context of this problem. You can't sell a negative number of cars, and you know, I don't believe we're going to have any kind of you can't sell a negative number of cars, and you can't have an income which is going to be negative. So we're just going to have a graph up here in the quadrant 1, the upper right-hand quadrant of our x-y axis. And we already discussed how the cars are going to influence how much we earn. The car is the independent variable, so the number of cars, you know, whether you write number or units of those cars, are going to go along the x-axis, and we're going to say, okay, this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Put some numbers on part of that scale. And then those cars are going to influence our income or our pay, and that is going to be in dollars. Okay, that's a little bit too sloppy. How about let's try that again. Our pay is going to be in terms of dollars. And now our income is going from, it's starting, the lowest it's ever going to be is going to be $1,000. But before I do that, let's go try and get my dogs to stop barking. Okay, yeah, I feel very safe from the salesman that was at the door. Now, our pay is ranging from, the lowest we're going to make is $1,000. So having my vertical scale start at 0 doesn't really make a whole lot of sense. Now, some teachers are going to want you to start this at 0 and then put like a little spacer here and then count 1,000. I'm just going to, it's natural that we just count by 200. So 1,000, 1,200, 1,400, and 1,600, and so on. But when you're making, when you're making graphs, it is acceptable to just, let the lowest value along your y-axis, just be appropriate for your word problem. So maybe I could let this lowest value be $800 and then put a tick at $1,000 and another tick to represent 1,200 and then 1,400, 1,600, 1,800, and 2,000 and so on. But do what your teacher wants. If they want you to put a 0 here and then that little squiggly line gap to indicate that you've skipped a portion of that scale before you start counting, then by all means please do what your teacher is asking you. What's really important though with making a graph is once you start a scale, you don't change that scale. I can't count by 200, 200, and then go, oh, okay, I'm going to count by 500s. That's very wrong. Okay, so we have 800, 1,000, 1,200, 1,400, 1,600, 1,800, 2,000, and so on and so on. And we've got a point, an x, y coordinate, an independent and dependent value of 0, 1,000, 1, 1,200, 2, 1,400, and this isn't on graph paper, so it's not going to be perfect here, 3, 1,600, and it looks like if I connect the dots, we are going to indeed get that linear function, as the title of the lesson, of course, implies. Well, there's the graph, and we have our scale. Probably would be best maybe if I just continue that on and so on. We have our units, our scale is the numbers. We have the labels on the x and y axis, the independent and dependent axis, with our value, our quantity, if you will, and the units of measure. And all that would be left maybe is to write on the top a title for this graph, our pay or our income as a salesman based on the number of cars sold. How can we identify this scenario as one that can be modeled by a linear function? Well, we have the graph now, and we can see the graph is straight. All right, so that's one way. If you have that at your disposal, or you have been able to make a graph, your graph is, well, linear. Now, another, and I'm going to kind of verbalize this and then step off and write it just to kind of speed the video up a little bit. Depending on your textbook, another thing to realize here is, as far as the language that they use, that might be called your successive points, or the difference between your points, which are consecutive in order. And of course, when they mean the differences between your consecutive points, 0, 1,000, 1, 1,200, 2, 1,400, and so on, that those differences between your consecutive points are equal. Now, when they say consecutive points, they're talking about this list of your domain values, your x values, are counting up by 1. And indeed, anytime you have a linear function, if the differences in your x coordinates are equal, you'll see a difference in the output values, the domain, the range values, your dependent values, your y values are going to be equal as well. Now, one of the textbooks I've taught from also calls this, when these values of x go up by 1, that those first differences are going to be equal. So let me step off and just write that, just to speed this up a little. Now, the last way of recognizing that, or another way of recognizing that a linear model is a good fit for your word problem is, it's not just these differences between successive points, or your first differences are going to be equal, but a line is straight. A line doesn't change any direction, and we know, hopefully you've studied it already, that, and if not, I'm going to let you now, the slope between any 2 points are going to be equal. So, like the next lesson I'm going to do with this type of topic, the values in our table are going to be a bit more scattered. So, we see that for each increase in of 1 on the domain value, the x value, the range values, the y values, are increasing by a fixed amount. But indeed, I guess what I'm saying is slope is rise over run, right? It's change in y over change in x. The real definition of slope is the change in y per 1 unit of change in x when you want to interpret it in terms of a word problem. And actually, that's how this table is set up. But indeed, we can see the slope is 200 here, and if I should be able to pick any 2 points in this table and get a slope of 200. So the slope between any 2 points or the slopes between any 2 points, all of those slopes that you can possibly do are going to be equal. Okay, now let's just try that. The slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And I'm going to let this be my, my second point, and this be my first point. And we've got 16 minus 1200 over 3 minus 1. That's going to be 400 over 2, and yes, we actually did, once again, as we see here, get that slope of 200. And now, I am pointing to the value in front of the x because this equation is in slope-intercept form. Y equals mx plus b. It's just that that order is turned around with the way that I have it written. Okay, so linear graph, differences between successive points or your first differences are equal and the slopes between any 2 points that you pick out of that table, you keep getting the same answer. That is indication that a linear model is a good fit. Now, one more thing. All of these first differences are 200. 1200 minus 1000, 1400 minus 1200, and so on. And then when we just pick 2 random points, we got, again, a slope of 200. And when you go back to the wording of this problem, the wording of the problem said that you were getting paid $200, basically, per car. You got a bonus of $200 for every car that you sold. Well, a lot of times in math, the word per is a division symbol. So if we write this as $200 per car, well, there is your change in y over your change in x, or at least an indication what should be on the y-axis, the domain, the range values, your dependent variables, that's what I wanted to say, over your, y over x, your domain values, or your independent variable. Again, slope is, in a different way of writing it, yet again, change in y over change in x, but you don't see delta notation really until you get to like pre-calculus or calculus textbooks. Now, one more question here before we start interpreting the slope and the meaning and context of this problem of the x and y intercepts. How many cars must you sell to make, $3,100? Okay, so you want your pay, you want your salary, not your salary, but your income to be $3,100. Well, it can be a little bit confusing to know where you put $3,100 when all you see in your equation are a bunch of x's and y's. But if you see here your pay is based off the number of cars you sell, well, I want my pay, I want my income to be $3,100. So $3,100 is equal to 1,000 plus 200 times the number of cars, which you could put x, or I'm going to write cars, because I think algebra is clear when you have words. We're going to identify where the variable is. The variable is on the right side of the equation now, so we're going to have to move everything away from c, x, or the word cars. And I have an addition of 1,000. 100,000 miles, whatever it is. No, we're going to subtract both sides by 100 to undo that addition of 100. So now I guess we're doing a little review of how to solve two-step equations. And then our last step is to, again, the question is how many cars must you sell? So we need to get the 200 away from the variable of cars, and that's connected by multiplication. So we're going to divide both sides by 200. And that is going to be, well, it looks like it's going to be, these zeros are going to cancel out, and 21 divided by 2 is 10.5. Now, there's a lot of applications, a lot of scenarios in the real world where decimals or fractions are acceptable and really kind of expected. But we can't sell a half a car. Okay, I guess if, salesmen can kind of like, 2 salesmen can work together to sell a car to a customer, but I don't want to get into that. We're talking about one person selling cars. You can't sell half a car. So if you sell 10 cars, you're going to be a little bit below 3,100, and if you sell 11 cars, you're going to make over 3,100. And so maybe, well, first of all, we're going to have to say that the number of cars you're going to have to sell, actually, let's put it in context. Really, your answers when you're dealing with word problems should be at least an expression of not a full sentence. So you need to sell 11 cars, because if you sell 10 cars, you're not going to make that $3,100. You're going to be a little bit below, but dust flying around. And if you sell 11 cars, I almost as I wrote a parallel sign, but if you sell 11 cars, you'll be just a little bit over that. But having a little bit too much money is much better than not having enough. Now, if I wanted to change this a little bit and say how many cars must you sell to make at least 3,100. This is why my videos always go long. I always think of like, well, what if it's this and what if it's that? And, you know, what if you see that in your homework? Well, if this is the expression that's your income from the sales from the dealership, and so I want this expression to be at least 3,100. So that expression of your pay can be equal to or more than 3,100, and I can just bring that down and bring that down. And now, instead of saying you need to sell 11 cars to make 3,100, you need to sell 11 cars or more to meet the requirements that is posed in this particular question. Okay, so now I'm going to clear all this off, and we're going to interpret the meaning of the, oh, you know what? I'm going to include something else at the end of this lesson. You can do this graphically as well. We have the graph, which is our pay. Pay is $1,000 plus 200 times the number of cars. We have the graph of a line representing the income. And we can also say that, going back to the equal part that I want to just make 3,100, you know, that can be equal to my pay, right? That's what I want my pay to be. And my pay is a value along the y-axis. So I could enter into a graphing calculator y is equal to 1,000 plus 200x, and y is equal to 31, I don't know why I just wrote a dot there, 3,100, and I'm going to go off the scale, right, because I only went up to 2,000. But I could graph y is equal to 3,100 and then use the intersect function of my calculator to find the coordinates where those two graphs intersect. And I'll do a little snippet at the end of our lesson to show you how you could have done this graphically with your calculator as opposed to algebraically. Alrighty then. Interpret the slope in the context of the setting or scenario. Well, I've already done that in Word, so I just wanted to write it. For every car you sell, your income will increase by $200. For every change, for every unit of change, or for every change in X, 1 unit of change in X, for every car that you sell, your, again, income will increase by $200. Because, yes, slope is rise over run. Yes, it's change in Y over change in X. But in terms of word problems, you need to focus on the definition of slope is the change in Y, $200 of income, per 1 unit of change in X. In that case, that's every car. And when you figure out what slope is and you simplify it to a point where the denominator is equal to 1, that will also be called unit slope. So basically, the statistical or word problem definition of slope is basically unit slope. Interpret the y-intercept in context of this problem. And I've already kind of done that in words as well. And luckily, we have it in our table. The y-intercept is where the graph is going to cross the y-axis. Well, when you're crossing the y-axis, the x is, well, 0. And we have a pay for when you sell 0 cars a month. Now, in this particular problem, the y-intercept has some real context. It is a very unsuccessful salesman, but it's not unreasonable or ridiculous to interpret this value of making $1,000 based on a sale of 0 cars. That's what it is. Interpret the y-intercept. You earn, or if it was a statistical problem that was modeled on real data, then you would say you would expect to earn $1,000 when you sell 0 cars. Now, I also teach AP statistics besides algebra and pre-calculus and calculus in my high school, and I've never had a statistics book ask you to find or interpret the x-intercept. But I noticed in one of the recent algebra books our school bought to use, it does. Okay, so we're going to find the x-intercept and interpret in the context of this problem. Now, often the y-intercept will not have any real-life meaning, and let's see if the x-intercept does. Well, to find the x-intercept, that graph needs to cross the x-axis, and I kind of already had a hint, gave you a hint earlier that I'm thinking as this line continues down and it seems like it's going to cross the x-axis on the negative side, X being the number of cars sold, we're probably not going to have a real-life context or meaning for this particular problem. But Y, in that case, the Y-axis is pay. If our pay is 0, that's going to be equal to, our pay is equal to 1,000 plus 200 times the number of cars that we sell. We're going to subtract both sides by 1,000. Get a negative 1,000 is equal to 200. I'm going to put, well, okay. I was going to say I'm going to put X, but that's only just because I don't feel like writing the word cars. We're going to undo that multiplication of 200 that's connecting that coefficient to the variable cars. Inverse math operation there. And we get negative 5 is equal to cars. Now, I'm running out of room to write a sentence, so let me just verbally say it. Our x-intercept is y is 0 when x is equal to negative 5. So if I were to sell a negative number of cars, if I were to sell negative 5 cars, my y-axis, which is pay, my income, would be equal to 0. Well, I already said that you're going to make $1,000 a month, period, unless, of course, the place fires you. And it's impossible to sell a negative number of cars. So for this particular problem, that would be how you would write it in context of the problem. I'm going to make if I sell negative 5 cars, I will make $0. That's how you write it as far as interpreting the x-intercept in context of this problem, but that doesn't mean it has any real meaning. That is how you model real-life situations with a linear function. I have another lesson coming up like this. I'll have a link in my description, but for now, I'm done. So I'm Mr. Tarrou. Bam! Go do your homework. Okay, so here we have our Inspire calculator up. We're going to go ahead and graph those two functions. Hit the tab button, or the toggle button here until we get to the graphing window. And our first equation was 1,000 plus 200 x. Hit enter. And we get what almost looks like a vertical line, but that's just because of the scale of our window for the application of this word problem. Now, we've already done the algebra, so we know that we need to sell, 2.5 cars, which is unrealistic, or 11 cars. So we're going to go to Window, Setting, and no reason to have negative x values when those x values represent cars that are sold, unless you just want to see the axis line on your screen, which maybe that's not a bad idea. So let's make that negative 5. And the calculator is probably going to have a problem because I hit the subtraction key. You have to be careful with this negative sign. Negative 5. There we go. And we're going to toggle down, make that, say, 15. Toggle down some more. Let's let that y-min be negative 100 just to see the axis line. And the vertical scale is going to be, let's set that to 3,400 since we're looking for a income of 3,100. And hit OK. Now we're going to go ahead and see, using those negative numbers, we include the XY axis. Hitting Tab to open up that entry line again, let's put in y is equal to 3,100, that income that we're looking to make in a particular month. We see that the graphs, like I drew on the chalkboard, are intersecting at a particular point. So we're going to go to Menu, Analyze Graph, and find the intersection. If you're working with an 83 or 84 calculator, TI-83 or TI-84, you can do second. There's a second button over here, and hit the Calculate button underneath the viewing window of your graphing calculator, and you'll find that intersection option in there as well. Where's the lower bound? Let's hit Enter. Let's put the cursor to the right of the upper bound of the intersection point, just basically move to the right of the intersection point. And there we see we have the same x-coordinate we found algebraically of 10.5. And because this is an application problem, because you can't sell 10.5 cars, we're going to say we need to sell those 11 cars to make the $3,100 of income. This is in scientific notation, 3.1 times 10 to the third power. So one last time, I'm Mr. Tarrou. Bam! Go do your homework.